It costs less than a used car. It has no pilot. And once it's launched, almost nothing can stop it from finding its target. This is the Shahed-136, a loitering munition that's become one of the most talked about weapons of the last few years. But how does something this cheap actually navigate hundreds of kilometers, and how does it know where to hit? In this video, we're breaking down the engineering behind it, how it flies, how it finds its way, and why it's so hard to stop. First, the basics. The Shahed-136 is what's called a loitering munition, sometimes nicknamed a kamikaze drone. Unlike a missile, it doesn't just fly a straight line to a target. It's designed to loiter, adjust course, and then dive into whatever it's aimed at, detonating on impact. It's small, a wingspan of around 2.5 meters, built mostly from lightweight composite materials and foam, which keeps both the cost and the radar signature down. And that low cost is the whole point. Instead of a multi-million-dollar guided missile, you get a weapon that reportedly costs somewhere in the tens of thousands of dollars, cheap enough to be launched in large numbers. What actually pushes it through the air is surprisingly basic. A small piston engine, similar in principle to something you'd find in a go-kart or a large model aircraft, not a jet turbine. This engine turns a rear-mounted propeller, giving it a cruising speed of roughly 180 kilometers per hour. It's slow compared to a fighter jet, but that's not the goal here. The goal is range and endurance. This design allows the drone to fly for hours and cover well over 1,000 kilometers on a single tank of fuel. The trade-off? That slow speed and that engine's distinctive buzzing sound are also exactly what makes it recognizable, which is why it's earned nicknames like moped or lawnmower from people who've heard it overhead. Now here's the interesting engineering problem. How does a cheap, mass-produced drone navigate accurately over hundreds of kilometers, especially in an environment full of GPS jamming? The answer is a combination of two systems working together. The first is satellite navigation, similar to the GPS in your phone, which gives the drone its general position at any moment. But GPS signals are weak and easy to jam. So as a backup, these drones are widely reported to use an inertial navigation system, or INS. This is a set of internal sensors, accelerometers, and gyroscopes that track the drone's movement from its very first moment in the air. By continuously measuring acceleration and rotation, the system can calculate its position even with zero outside signal. The same fallback principle used in submarines and early cruise missiles. In practice, that means even if GPS is jammed or spoofed, the drone can often still find its way to a pre-programmed set of coordinates using inertial guidance alone. Though accuracy tends to drift the longer it flies without a GPS fix to correct it. Rather than being remotely piloted, these drones typically fly a pre-programmed route, a series of GPS waypoints entered before launch. The onboard flight computer follows this route autonomously, adjusting the control surfaces, the small fins at the rear, to correct heading, altitude, and speed along the way. This is one of the reasons these drones are so effective at overwhelming defenses. They don't need a live human operator flying each one individually. A single team can launch a whole batch, each with its own coordinates, and let the automated systems handle the rest of the flight. So how does it actually hit something? Once the drone approaches its final programmed coordinates, it shifts from level cruising flight into a steep dive toward the target point. The warhead is mounted in the nose, and detonation is typically triggered on impact. It's worth noting that these are largely considered coordinate-guided weapons, rather than ones using real-time image recognition to pick a target mid-flight, meaning accuracy depends heavily on how precise the pre-flight coordinates were, and on how much the inertial system has drifted by the time it arrives. This is where the engineering gets clever from a cost standpoint. Traditional air defense, surface-to-air missiles, radar-guided systems are built to intercept fast jets and cruise missiles. But this drone flies low, slow, and has a small radar cross-section, which can make it harder to detect early with systems tuned for faster, larger threats. And the economics matter too. Firing a missile that costs over $1 million to shoot down a drone that costs a fraction of that is a losing trade if it happens over and over. That's part of why cheaper countermeasures, like machine guns, mobile gun systems, and short-range interceptor drones, have become a growing focus for defenders. What makes the Shahed-136 significant isn't really the sophistication of any one system. GPS navigation, inertial backup, autopilot waypoints. All of these individually are decades-old technology. What's significant is the combination, taking mature low-cost components and packaging them into a mass-producible weapon. It reflects a broader shift in modern warfare, toward cheap, autonomous systems produced in large numbers rather than small numbers of extremely expensive precision weapons. And that shift is a big part of why militaries around the world are now racing to develop cheaper counter-drone systems of their own. So that's the engineering behind one of the most discussed weapons of the last few years. Not because any single part of it is revolutionary, but because of how cheaply and effectively those parts were combined. If you found this breakdown useful, subscribe to AeroDrive. Every week we break down how real-world machines, vehicles, and systems actually work. Thanks for watching, and I'll see you in the next one.